So looking at the figure, it states that figure 1 shows a sketch of part of the graph of y equals gx, where the function gx is given by 3 plus the square root of x plus 2. And this is obviously valid for x greater than or equal minus 2. A. State the range of g. Okay, so what exactly is the range? Well, we know that range is pretty much all the values that g can actually take for a given domain. And since our given domain is x greater than or equals minus 2, we can observe that the minimum range just by looking at it graphically is at the most negative point, or the least negative point as we should say, and that's at x equals minus 2. So here's a little dotted line, so minimum range should be there. Now of course, if that's the minimum range at x minus 2, then all we do is of course plug in x minus 2. Then g should give us 3. And that's it, guys. We know clearly that the minimum range for g is 3. So g takes values anything greater or equal than 3. Okay, not bad. So let's move on to part B. So here we're supposed to find the inverse function of g and state its domain. Now, what I stated is that we should of course let y equals the inverse of g and then rewrite the function in the following way. So basically all you really want to do is flip gx with the letter x and flip x with the letter y. So the function looks a bit like this. Okay. Now, all you want to do is just solve for y, because we know that y is going to be the inverse. So subtracting 3 across and then squaring the left hand side and right hand side, of course, that function, and of course, and then finally subtracting 2, we should get the inverse function here. And the one special property about these inverse functions and functions, that we know that the domain of the inverse is equal to the range of the original function. Likewise, the range of the inverse is equal to the domain of the original function. Hence, we can say that the range of the inverse is greater than or equal minus 2, and its domain is greater than or equal than 3. Voila. Not so bad at all. Alright, so part C. Okay, so find the exact value for x which satisfies the function gx equals x. So guys, this is just a bit of algebra. So let's tackle it down. So let's try and solve the following equation for x equals 3 plus root x plus 2. So what I did is just subtract 3 across and then squared both sides, which will give us x minus 3 squared equals x plus 2. And then expanding the quadratic on the left will give us x squared minus 6x plus 9. And then of course subtracting x and 2 from the right to the left will give us finally the following quadratic expression, x squared minus 7x plus 7, all equal to 0. Now, using the quadratic formula, this is what we should get. So plug in all the figures in, it should look something like this on your calculator, and then finally you should get x equals 7 plus minus root 21 all over 2. And now, since x must be greater or equal than 3, which of course satisfies the inverse property and so on, we should therefore get x equals 7 plus root 21 over 2. The thing is, if we chose a negative value, it would be less than 3, so that would not be the valid solution. That would satisfy the function itself. And of course, it will cause a problem. And lastly, D. Hence, state the value of a for which the following function of g is equal to its inverse. Now, if we kind of look back, we can clearly see that from part C, it said that gx equals x. So clearly, if gx equals x, that means ga equals a, which also equals the inverse a. So in fact, all three equal each other. If that's the case, that means all these functions must equal a. And the previous solution, we found that gx equals x. And x was 7 plus root 21 over 2. So clearly, a equals 7 plus root 21 over 2. Now, to check if this is correct, well, you don't have to check. You just say state, so it's 1 mark. You can tidy the following polynomial. So I just did a little extra working. So you don't necessarily need to do this, but this is just for the enthusiast. So if you want to solve this completely, you can make ga equal to the inverse of a. And then expanding, rewriting the function and expanding the left and the right, you'd eventually get a fourth power polynomial. Now, you can't actually solve this directly without using an educated guess or knowing at least what solution of one of its values. Of course, we know the first solution would be a equals 7 plus root 20 over 2. And really, if you just stop through that, then of course you're going to get a nice, lovely 0. And that's it, guys. We are trying to find the values of r and alpha, and in order to do this, looking at the question, it tells us to write the following trigonometric expression in the form of r cos theta plus alpha, where both r and alpha are constants. Now, in order to do this, the easiest way to tackle this is to firstly realize that we can equate, and we should know is that 5 cos alpha minus 2 sine theta is identical to the r expression. That is, we can say let 5 cos theta minus 2 sine theta be identical to, and then all we have to do is expand the cos theta plus alpha expression into the full angle equation, or the double angle. So it should be known, it can be written as r bracket cos theta times cos alpha minus sine theta times sine alpha. And now from here, we're just simply going to equate the coefficients. So notice on the left side, we have a cos theta on both, and we have a sine theta on both. So in terms of cos theta, we can say 5 cos theta equals r cos theta times cos alpha. Cancelling down the cos theta should give us r cos alpha equals 5. Likewise, we repeat the same process for sine. Because they both have negative, we can ignore that and say 2 sine theta on the left hand side equals r sine theta times r sine alpha on the right hand side. Once again, eliminating the sine theta should leave us with r sine alpha equals 2. Alright, now at this stage we need to figure out how to find r and alpha. So one cool technique we could use is a nice trigonometric identity. We know that firstly sine over cos equals tan, and if we do r sine alpha over r cos alpha, we can easily cancel on r, so we'll be left with exactly tan, and this is of course equal to 2 over 5 from both equations. And all you have to do simply is now make sure your calculator is in radians and simply tan inverse 2 over 5, and that should give you 0.381 radians. That's it. Now as for r, how to do r? So actually for r, all we can do is use two ways, but in this case we're going to use a trigonometric identity. First things first, we should know off the bat by now at least that sine squared alpha plus cos squared would always equal 1, at least if they're both alphas. So therefore, since we know that cos alpha equals 5 over r and sine alpha equals 2 over r, we know that this full expression can work. So just literally popping in the values. So we have sine squared alpha, which is literally 2 over r all squared, it gives us 4 over r squared, plus cos squared alpha, which is just squaring 5 over r, which is 25 over r squared, and all of that equals 1. And that's it, guys. Now we just add up the fractions. This should give us 29 over r squared equals 1, and then therefore we should get r squared equals 29, and hence r equals plus minus root 29. And if you remember from the question, it tells us that r has to be positive, so therefore the only positive answer is r equals root 29. Now the best way to do this is to realize that we're trying to get a cos and a sine, and of course we start with a cot and a cosec. So first things first, I would convert everything into cos and sine. So what is cot 2x? Cot 2x is literally the same as the opposite tan. So instead of sine over cos, it's cos over sine, and of course they're both 2x. Now as for cosec 2x is the same as 1 over sine 2x. And that's it, guys. All you want to do now is substitute back in and see what happens. So replacing these two with the following identities, we should get 5 times cot 2x, which is, oh my god, this warning is annoying. Cot 2x, which is the same as cos 2x over sine 2x, alright, minus 3 times cosec, which is 1 over sine 2x equals 2. Now, what happens here? So, notice how we got sine 2x at the bottom. So what I will do is just multiply everything by sine 2x to clear it. So we're going to end sine 2x over here. So we're going to get 5 cos 2x minus 3 equals 2 sine x. 2 sine 2x, and therefore rearranging it so it looks like this, subtracting this and plusing 3, we're going to therefore get 5 cos 2x minus 2 sine 2x equals 3, and therefore the value C is 3. Okay, part C. So hence or otherwise solve within the following range between 0 and pi for the following equation, which we already found out can also be written like this, giving you answer to 2 decimal places. Now, just looking at this head on, we should know that we cannot actually solve this easily in its current form. This is why if we look back at part A, which I should have over here, we were able to find out that this equation can be rewritten in this form. And if you notice, the thetas here are actually simply substitute for 2x. So the 2x here and the theta are actually the same. So we can say that this equation can be rewritten as r cos, instead of theta plus alpha, it's going to be 2x plus alpha. And this is all, of course, equal to 3, because that's what we're dealing with. Now, what were the values r? Well, r was found to be, I believe, root 29 cos, and then we got 2x plus, and then the alpha here, I think, was 0.381 radians. Okay, equals 3, and yeah, now we just simply solve this. So all we can do is just divide it by root 29 and then cos inverse. So this should give us 2x plus 0.381 equals the cos inverse over 3 over root 29. And if you enter this in your calculator, remember to always keep your solutions in radians. You should get a solution of 0.9799. So let me put on this side. So therefore, all of this expression here, 2x plus 0.381 should equal, okay, 2 decimal places, yeah. So let's just say 0.98 radians. So that's our first solution. Now, and of course, now the easy part is literally throwing this in a cos diagram. So doing a cos, so it's kind of hard to do neat here. I could use the straight edges, but it's fine. This can be rough. So using the cos diagram, we should know that we're working with cos. So this means C is positive and A is always positive, and they both have an angle width of what's it? An angle of 0.98. Right, and remember this applies for from the range of 2x. So because we're working with this entire range here, therefore we can kind of expand this by adding firstly adding 0.381 across, doubling it first and adding 0.81. So our new range is 0.381 greater equal than 2x plus 0.381 less than 2 pi plus 0.381. So this is our new kind of interval for the cos. Yeah, so this is where we can actually go now. And just for the sake of making it easier, 0.31 is less than this value, so we can only do 2 circles. So our only solutions, of course, would be the one we have and all the way around here, which is 2 pi take away this value. So our second solution is 2 pi minus 0.98. Now, to find the value of x, all we have to do now is just solve this equation. So this tells you that the two solutions are 0.98 and 2 pi minus 0.98, which equals to this equation here. So all we have to do now is subtract 0.381 to both of these and divide it by 2. So hence, the first value x should be, I should have done it beforehand, 0.98 minus 0.381, all divided by 2, should give us, firstly, 2 decimal places, 0.30 rounded up. And for the second one, first we got 2 pi minus 0.98. Now we subtract against 0.381 and divide it by 2, and we should get 2.46. 2.46. Hey guys, welcome back to another of my videos. So in this one, we'll be looking at question 5 and we'll be tackling part A. Okay, so what do we have here? So we're given a figure where we can see that there's a curve intersecting with a straight line. And this curve is given by this y equation here for x greater than minus 2.5. Alright, so what do we know? So we know that the point P of x equal to minus 2 lies on C. Okay, so we know this one has an x coordinate of -2. Let's just say -2 question mark. Okay, and that's literally what we're given. And we need to find an equation of the normal to C at point P. So the normal of the curve at point P, where we know x is -2. And this has to be written in this form. So the final form is no big deal. The whole point is understanding the equation of normal. So the first thing you want to do, of course, is find the equation of tangent. And then after that, use the perpendicular gradient, and you've done it. So let's do it. So first step is to write this form, y equals mx plus c. Okay. Next, then all we need is the perpendicular gradient. So what is the equation of normal at this point? So we know the x coordinate is -2. So I think it's best to find the value of y, right? So to find the value of y, all we do is plug in the x value into this equation here. So we're going to have y equals 2 log. And then plug in x -2 and get -4 plus 5, so log 1. So log 1 is actually 0. So this is actually pretty useful. Minus 3 times -2 over 2 would cancel out, and you're left with a positive 3, so it'll be plus 3. So therefore, the coordinates at P is going to be -2 and 3. Sweet. All right, not so bad. Now, how to find the gradient? Okay. All right, so to find the gradient, actually, all we need to do is differentiate this equation, because remember, the gradient is the change in y with the change in x, which is the derivative of this. So let's find dy dx. So dy over dx, what's it going to be? Okay, so to differentiate the log function, all you have to do, so let's write the 2 first, constant. Differentiate the log function, you differentiate the inside and divide it by itself. So the derivative of 2x plus 5 is just 2, and then you divide it by 2x plus 5. That's literally all you do. Next, minus, and the derivative of 3x over 2 is just 3 over 2. Now plugging the value of x so we can get the actual gradient. So at x equals -2, the gradient m, so this is the regular gradient, the gradient for the tangent, not the normal. It's going to be 2 times, so it'll be, so this will simplify to make 4. So you can, just smash this in your calculator. You'll get -4 plus 5, this becomes a 1. So you get 4 minus 3 over 2. And then all you have to do from that point, so 4 minus 3 over 2, you should get 5 over 2, which is your tangent gradient. And then at this stage, finding the perpendicular gradient, you're just going to do the perpendicular gradient. All you have to do is just find the reciprocal and flip the signs. So it's going to be -2 over 5. And voila, guys, plug all these values for m back in here, x and y back in here. And yeah, and then solve for c, and then all we have to do is just rearrange this. So therefore, plugging in all the coordinates, you're going to plug in 3 for y, so you get 3 equals m, the negative gradient, which is -2 over 5, times x, which is -2, plus c. Now solving for c, what should we get? So this becomes plus 4 over 5, so it'll be 3 take away 4 over 5, and this should give us a c value of 11 over 5. All right, cool. So I guess we're almost there. So now all we do at last is just plug in the grade. So now going back to the gradient equation. So let me just make a fresh page. Oops, don't need something like that. So what do we have so far? All right, so we have going back to y equals mx plus c. Therefore, our final equations be y equals the gradient, which we said was -2/5, and c is 11 over 5. -2/5 x plus 11 over 5. Multiply the whole equation by 5 to get rid of the fraction. We're going to get 5y equals -2x plus 11. And finally, making it into ax plus by, plus in 2x to give us 2x plus 5y equals 11. And that's it, guys. Hope this video, and that's it, guys. So we're going to look at part B now, yeah? Alright guys, here we are, part B. So in this case, we need to show that the x coordinate of Q at this point here is the solution given by this. Okay, so in this case, we're not actually trying to find x, we're trying to present some kind of equation in terms of x. Because actually looking at this right now, it's quite difficult to solve without iteration methods. So what do we have here? So what do we know about Q? So we know that the curve and the line intersect both at points P and Q. So because they intersect, we know that the line equation can be simultaneously solved with the curve. So how about we substitute the curve into this equation here, yeah? So that'll be the first step. So that means, let's just start from here. We can say therefore 2x plus 5 multiplied by all of this would equal 11. So let's just simplify that all out. So we get 2x plus, now multiplying this by 5, what do we get? We're going to get 10 log bracket 2x plus 5 minus 15x over 2, and all of this equals the right hand side, which is 11. Now, just trying to mash everything up, I think what the best way to do is to keep all the x terms on the left and the log x terms on the right. Okay, and then move, and then partition x. So let's clear the x terms. So we got 2x, take away 15x over 2 will give us a negative 11x over 2. And subtracting 10 log x across, we're going to have 11 minus 10 log 2x plus 5, and just flipping the signs over actually, because we want this to be positive, don't we? So actually no, first let's multiply by 2 and then divide by negative 11. So multiplying by 2 and dividing by 11, we're going to get x equals 22 minus 20 log bracket 2x plus 5, and dividing by negative 11, we're going to have minus 11 here, minus 11. Therefore, x, just tighten this up, you can see that this becomes minus 2 and this becomes plus 20 over 11, just like we have here. So yeah, and therefore, so now we're going to get exactly 20 over 11 log 2x plus 5, all subtracted by 2. And that's it, guys. That's pretty much what you have to do. And so yeah, so if you have any other questions, let me know. Otherwise, we're going to move on now. So see you in part C. Okay, part C, guys. So this one, oh my god, this is very easy. So let's have a look. So given that x1 equals 2, find the next two values using the iteration form below. So if you haven't seen iteration, all you literally do is just plug in, get a result, and then plug the answer to the next equation and get the third result. Easy, really, very easy. So what I already found the solutions to this, but anyway, I'll just show you how it's done in case. So let's have a look. So to find x2, you literally just plug in x1 here. So we're going to get 20 over 11 times the log of 2 times x1. So x1 value is 2 plus 5 minus 2. And whatever the answer is, oh yeah, before you do this, I recommend that in your calculator right now, type the value 2, because x1 is 2. Press the equal sign, and then this should be saved as your answer. And then when you type this formula, make sure you type it and just use the answer value. So here, so just type the answer button here. So every time you press equal, it will automatically generate the next answers without you typing the whole formula again. So yeah, when you put this in the calculator, you should get an answer of this, which I wrote, which is 1.9950. So x2 is about 1.9950, because basically I didn't write this in the question, but you need your answers to 4 decimal places. Now do the same for x3. So for x3, we're going to have 20 over 11 times the log of 2 times x2 plus 5 minus 2. And again, using your answer value, which should already be there, you just literally press equals again, and your answer for x3 should be 1.9929. And that's it. 929. That's really it, guys. Nothing more to iteration. You just plug and go. So anyway, I hope this video helped, and let me know if you've got any more problems to look at. Other than that, I shall see you guys soon, and take care. Ciao. Okay, given that a and b are positive constants, on separate diagrams, let's try and sketch the graph with these following equations. Okay, so the first thing you want to know is that we're dealing with absolute functions. So this means that when you have a function of x, which is absolute by the two absolute signs, this means that the result of this function x will guarantee that the value of y will always be positive. This means that the solution on these axes, at least for the first case, is going to appear on these two quadrants. It will never come down here. So if it was to cross through the x, it would have to reflect. That's what it means. It means the solution of y will stay positive. So the best way to do this is to see what kind of shape we're dealing with. So let's have a go plot some examples, some figures. So we can say when x equals 0, what do we get? We should get when x equals 0, we should get y equals the absolute value of minus a. So let's just stick with the non-absolute, yeah? Let's pretend there's no absolute sign. So y should cross at minus a, which is, let's say here. Okay? Now how about when y equals 0? Well, when y equals 0, we should get 2x minus a. So plussing a and dividing by 2, we should get x equals a over 2. And that should be around, let's say around here. So let me just mark up something here and call this a over 2. Now all we have to do is draw a straight line. So in this case, this is quite easy. So let's get our ruler out. So draw a straight line. Okay, so it should be crossing from here. So something like this. Except the only difference now is that this part of the line would be faded out. So we could actually reflect it. So what we could do is that this line here could be the dotted version. So instead of crossing through here, we're going to reflect it upwards over here. So let's make another marking of it. So it's about 5 down. So let's say 5 down here. So now we just reflect it simply. So adding another straight line, connecting from here all the way to here. And that's it. That's literally done. So the whole purpose is to reflect the line. So I could just make a dot line right now, in fact. So this is the point of reflection. Well, let's say it's here. Okay, and let me just label these properly. So we said this was a over 2 minus a, so this would be positive a, and this will here a over 2. Now for the second equation, it's the same thing, except now we've raised the whole equation, the whole system by plus b. So this entire shape will be reflected here, except it's raised by level b. So literally I would just copy this entire shape. So let me just copy and paste. So copy this and just copy this. So shift control. So you want to do the same thing here. So instead of it being here, it's going to go up by a level of, say, b. Let's just say b was here. So it's gone up by additional factor of b. So let's say this height is increased by plus b. Okay, so this means it's going to hit here at a plus b. And of course, this point here now is going to be a over 2. The corner of this point is, of course, still a over 2. And this height is an additional plus b. And that's it. I think we are pretty good here, aren't we? Oh yeah, the corners to each point. So again, this a over 2, b. And that's it. Let's move on to the next part. Okay, part b. So given that the equation is now extended to this one, so we have 2x minus a all absolute plus b equals 3 over 2x plus 8. And we know that this has a solution at the points x equals 0 and x equals c. So here they just want us to find c in terms of a. Alright, so what is the first thing we need to know? We need to know that the absolute value can be written in two ways. Firstly, is that the solution here is always going to remain positive. So this can indicate that, firstly, 2x minus a could be positive, or x minus a minus 2x is also positive. So the whole thing is positive. So our initial thing is that we can actually rewrite all of this as either one of these two equations. So in general, we can say that the first equation could be the first one, so 2x minus a plus b equals 3 over 2x plus 8, or we could have the second case, which is a minus 2x plus b equals 3 over 2x plus 8. Now, all we have to do is plug in these coordinates. So plug in x equals 0 and x equals c. So let's have a go. So let's do x equals 0 firstly for both cases, yeah? So when x equals 0, what do we get? Well, we're going to get minus a plus b. So this would be minus a plus b equals, so 3 over 2 cancels out and equals 8. So we can say therefore b equals 8 plus a. Or, in this case, if we did the same thing here, this will cancel out and then we're left with a plus b equals 8. So we have two arguments, okay? Now, how about if we chose, let's try x equals c for now, yeah? Let's see what we get. So when x equals c, we should get the following. So we should get 2c minus a plus b equals 3 over 2c plus 8. Okay. So in this scenario, you'll notice that this will collide. So what we would do is that we wouldn't use x equals c for the first equation. We would use x equals 0 for one and x equals c for the other one. You see? So we're going to cancel this out and then start right here. So say when x equals c, what does this equation become? We're going to have a minus 2c. So let's do it quick. A minus 2c plus b equals 3 over 2c plus 8. We know what b is. So remember, we want to write this answer in terms of a. So this c has to, so the b needs to be eliminated. So we know b is 8 plus a. So let's pop it in. So therefore, we're going to have a minus 2c plus b becomes 8 plus a equals 3 over 2c plus a. Now, moving c to the left side and everything else to the right. So that's minus 3 over 2c across. So minus 2 minus 3 over 2 would give us minus 7 over 2c. So minus 7 over 2c. A plus a is 2a plus 8 equals 8. Subtracting a will give us 0, and then subtracting 2a, so we're going to have minus 7 over 2c equals negative 2a. And finally, timesing by 2 and dividing by minus 7 should give us a c value of 4 over 7a. And that's it. I believe this is the final answer. And let me know what you guys get. Compare with me because there's no actual general solution. So the main idea, of course, is to pick one solution and pop it into the other one. Okay, if you did it in reverse, if you start with the right hand side, let x equals 0 here, and let x equals c here, then you should get the same result, assuming there's no calculation mistakes. Okay, other than that, guys, I believe this is it, and yeah, I shall see you guys soon, and ciao. So we're given a function given by y equals 2x all multiplied by x squared minus 1 to the power 5, and we need to show that the derivative is given by this function here, and then hence we need to find the set of values x which the derivative itself from part A is greater or equal than 0. So looking at part A first, how do we get this? So this is just a simple case of differentiating, so not too bad. So we need to do this using the product rule. Okay, so let's look at part A again. So by the method of the product rule, we just have to label some terms. So we can call firstly 2x u, and we can call v the second term, which is x squared minus 1 to the power 5. Okay. In turn, there's something known as the fast product rule, but for the sake of accuracy, we'll do it like this. Now all you have to do is differentiate both. So let's call this one u prime, which is a derivative. So the derivative of 2x will give us 2. And the derivative of v, well, we need to use the chain rule. And the chain rule tells us that we have to differentiate the inside of the function and then drop the power. So the derivative of the inside is just 2x. And then dropping the power would be multiplied by 5. And then we decrease everything. So this would be x squared minus 1. And the power decreases by 1. So it's 4. Okay, easy. And then 2x times 5 is, well, 10x. So let's just tidy this up. So we've got 10x all multiplied by x squared minus 1 to the power 4. Hence, by the product rule, all we need to do now is simply connect these. So we could say firstly that the product rule tells us that it's going to be u times v prime plus v times u prime. So the final solution is uv prime plus vu prime is going to equal to 2x multiplied by this function here, so 2x times 10x will give us 20x squared, bracket x squared minus 1 to the power 4, plus, now next one, v times u prime, so this quantity times 2, we just literally glue together to get 2 times x squared minus 1 to the power 5. Now, the function wants us to keep in terms of power 4. So we need to reduce this power by 1. So what we could do, we can partition this as to the power 4 and to the power of 1. So let's drop this power to 4 and stick another one next to it. That's it. And now we just collect like terms. So let's collect in terms of x squared minus 1 to the power 4. So this will tell us that we're going to have, therefore, in terms of x squared minus 1 to the power 4, we should have, on the left side, firstly, we have 20x squared. Okay, so this is just factorizing. Plus, on the right side, we're left with 2 times x squared minus 1. And if you expand it, we're going to get 2x squared minus 2. And lastly, now again, collecting like, tidying this up for the final part, we should have, making it, putting in front actually, so we have a gx in front. So this is our gx. This will summarize to 22x squared minus 2. So we're going to have bracket 22x squared minus 2 equal multiplied by x squared minus 1 to the power 4. And that's it, guys. Our gx is therefore 22x squared minus 2. Okay, so let's have a look at part B now. So from part B, and keeping the derivative on the next page, we need to find the set values of x for which this derivative is greater or equal than 0. So all we can literally write is greater than or equal than 0. And yeah, this is just a case of solving now. So let's have a go at solving this. Okay, so we can split this into two parts. We could say firstly that 22x squared minus 2 is greater or equal to 0, and the second term is greater or equal to 0. Let's write it down. So 22x squared minus 2 greater or equal to 0, or x squared minus 1 to the power of 4 is greater or equal than 0. Oh, so this looks like a difference of 2 squares, and this one also looks like a difference of 2 squares in fact. So let's see what we can show here. So because it's greater than 0, firstly, we can plus 2 across and divide by 22. This will give us x squared is greater or equal than 2 over 22, which is 1 over 11. And it's just square rooting this. So because the function is greater, this will tell us that if we imagine a derivative curve, then this would mean that the answers are going to be on the outside of the curve. So let me just try and draw a simple sketch. So I'm not going to draw this accurately because we need more points. So suppose the curve is something like this or something. Because the function is greater or equal than 0, that means we're interested in the outer part. So for example, this range here, any function which is greater than 0. So this means that the solution, if we can square root this one, the results will be outside these intervals. The same applies for here as well. So basically, square root this one will give us plus minus 1 over 11. So root 1 over 11, so x here. So this point here would be x equals minus square root of 1 over 11. And this point here will be x equals positive root 1 over 11. Okay, so far this is what the ranges of values can take. Now how about the one over here? Well, first things first, because it's powered by 4, we can assume there's 4 quantities, so we can ignore that. So then therefore we're left with x squared minus 1 greater or equal than 0. And this is a difference of 2 squares, so therefore x would therefore be, x squared would be greater or equal than 1. Same rules apply, except now that on the left hand side, we accept values which is less than minus 1. Square root this one is 1, and on the right side we accept values are greater than positive 1. However, this interval is these surds are smaller than this one, so in fact the minus 1 and 1 is included in the gx part. So therefore we can say that the final range of solution, because remember minus 1 is somewhere here and plus 1 is somewhere here, so the final solution is going to be x, hold on, let me try and make it in a neater way. Therefore we can say x takes values less than minus square root of 1 over 11 or less than equal, or x takes values greater or equal than positive root 1 over 11. And that's it. Now let's move on to the final part. Okay, so the final part, question 7. Arguably, I think this was the hardest question in the paper by far, because you actually need to do a lot of trig identities, and you kind of need to use implicit differentiation to actually work out this derivative of y. So let's have a go. So I'll show you my way. In fact, there are two ways to solve this, but I'm going to show you an easier way. Okay, so without further ado, let's go. So given that x equals the log of sec 2y, find its derivative in terms of x. So the first thing first is that I would want to get rid of this log function and by multiplying, by taking exponential on both sides. So over here we could say the log, taking exponential on both sides, we should get ex equals sec 2y. Next, I would like to rewrite this as 1 over cos 2y. So we're going to have ex equals 1 over cos 2y. The main idea is to always work in terms of sine and cos, because you can get every single answer. Sec, tan, etc. are can be kind of confusing. Now what we want to do here is to multiply cos 2y across, and then we're going to get cos 2y ex times ex equals 1. Now I'm going to stop it for a second, and I'm going to define cos 2y. So we can, if we're going to define cos 2y, we could divide e to the power x across, and this will give us e to the negative x. So up here, I'm going to say let cos 2y equals e to the negative x. This is going to be very handy later, and I'll show you why. Now let's go back to the original problem. So over here, I want to differentiate this using implicit differentiation. Okay. Yes, implicit. So first things first, we're going to use the product rule to deal with the left side and differentiate the one later. So using the product rule, the quick way to do it is to just differentiate the first term, then copy the second, plus copy the first term, then differentiate the second. So the derivative of the cos 2y will give us a negative 2 sine 2y times dy of dx. Remember, because it's a y term, the derivative of the 2y will become 2 dy dx. Okay? And then you copy the ex. Plus, now we copy the cos 2y. And we differentiate the ex, which is ex. And to differentiate the 1, well, it's just 0. So, what do we do here now? So now we have our derivative. We can rewrite this in terms of dy over dx. And before that, we can cancel out any common terms. So let's cancel out ex, because that's gone. Next thing we want to do is to plus 2 sine 2y dy dx across and divide the whole term by 2 sine 2y. So rewriting everything, you should get something like this. Dy dx equals cos 2y all over 2 sine 2y. Put a bracket around them. Now, do you remember earlier when I said let cos 2y equals e to the negative x? Well, this is going to be useful. So now we can finally find what sine 2y is in terms of x and cos 2y, because we know what cos 2y is. So the fastest way to do this is to use the most popular trig identity. And that's it, guys. That's to say, let sine squared, let's call it sine squared theta plus cos squared theta equal 1. And now we know what cos theta is e negative x. But let's solve this in terms of sine, yeah? So if we're going to find the sine theta, we can subtract cos squared theta and then square root. So we're left with something like sine theta equals 1 minus cos squared theta all square rooted. Now, theta in this case, it will be 2y. So this means that, it's right here, sine 2y equals 1 minus cos squared 2y all rooted. Cos 2y is e negative x, so that means cos squared 2y is e to the power of negative 2x. So this is e power minus 2x. So we can write the top here. So therefore, sine 2y equals the square root of 1 minus e negative 2x. And that's it, guys. Plug both of these into the final equation, and you're going to get, therefore, dy dx equals e negative x all over 2 times the square root of e minus e negative 2x. Voila. And yes, this works. I tested it with another method, which is using cot, but yeah, this is the way to do it, and hopefully you guys got something like this. Okay, so what does the question tell us? So over here we're given a nice figure 3, which is showing a curve with 2 points, point T, PT, which seems to be the turning point. So probably the highest point on the graph too. And the statement states that the number of rabbits on an island is modeled by the following equation. And we see the equation has exponentials and negative exponential powers. And this is all for t greater than or equals 0. So we just have to assume that this is most likely time. And yeah, it says where p is the number of rabbits t years after they were introduced onto the island. Okay, so part A. Calculate the number of rabbits that were introduced onto the island. So if you want to calculate the number of rabbits that were introduced, this is probably from the very beginning of time. And the very beginning of time is obviously at time 0. So what they want us to do is literally plug in t equals 0 into that equation. And when you do that, you should literally get this. So we can call this PO, represent times the population at time 0. And if you do this, if you bust this in the calculator, you should get 65 rabbits. And that's it, literally done. One more question. Now let's jump on to part B. So here we'll be trying to figure out the derivative of p with respect to the time variable t using that given equation that we have. Now, how do we differentiate this one? So as you can see, just ignoring 40 for a second because we know that derivative of a constant is 0. The equation we have, a fractional equation, we could actually use the quotient rule. And if you remember, the quotient rule, we need two variables, u and v. And it's given by v times the derivative of u minus u times the derivative of v all over v squared. Okay? And at this stage, we just have to label the u and v. So I personally, and pretty much every single math textbook does, they label the top half u and the bottom half v. And here we are. Now, to differentiate u, simply to differentiate exponential, we literally differentiate the power part minus 0.1 t and just drop the 0 minus 0.1 down and multiply it to the 100. And that should give us negative 10. And of course, we copy the exponential part. Likewise, for v, differentiate 1, you get nothing. Differentiate 3 to the power minus 0.9t, well, you drop minus 0.9 down, times the 3, you should get minus 2.7. And of course, the exponential part. And that's it. Now we just plug all of that into the dp over dt equation. And we should get the following. So, I mean, it's all a matter of construction. I try to be quite skillful with it. So, if you're dealing with a longer term with 1 plus or minus something, I tend to put that second. So v times u prime, I did minus 10e first. I did u prime times v first because it's just easier to write. And minus, so notice that you got negative 2.7 for v prime. Well, if it's a negative, I'll put that first before the u. So I'll plus 2.7 e to the power negative 0.9t. Then I times this against u, which is 100e power minus 0.1 t. And literally smash this all over v squared. And v squared is just 1 plus 3 times exponential all over power 2. And literally this is the end of the answer. Now all they really want you to, all that you're probably expected to do is just tidy the top line. So first things first, let's expand the brackets and multiply out the right hand side. So we should get minus 10e power minus blah blah times 1 is the same, minus 30e to the power minus t. So remember, minus 0.1 t times minus 0.9 t, you add the power, so minus 0.1 plus minus 0.9 is just minus 1, so just minus t. And likewise, plus 270e negative for the same reason. Oh man, that's a lot, right? It's a lot of reading, guys, isn't it? So just have a look. Next one, so minus 30 plus 270 give you 240e minus t, and of course minus 10e power negative 0.1 t. And lastly, we can factorize 10e minus t out, and we should get the following. Voila, that's it. Man, this can really drag your breath out. So I hope this helps, guys, and for those continuing, get ready for part C. Alright, what do we have here? So it states that the number of rabbits initially increases, reaching a maximum value given by pt, as we saw earlier in the graph, when small t equals capital T. So capital T is clearly the maximum. So using your answer from part B, calculate the following. The value of t to 2 decimal places and the value of pt to nearest integer. So really, let's understand this. So when we differentiate, firstly, we should understand that the curve we saw in figure 3 is literally the turning point. And this turning point for any derivative, any shape, is always when the gradient is 0. And we know that the first derivative is the gradient. So setting that to 0, we have the dp over dt equal to 0. Therefore, we can solve that equation. So notice that this bottom half of the fraction multiplying against 0 will cancel out. And you're just left with the following: 10e minus t times 24 minus e to the power 0.90. So the first solution, 10e to minus t equals 0, is no solution, of course, because taking logs, well, you can't have a log 0. Ignoring that, so taking the second solution, 24 minus e to the power 0.90 equals 0, well, just doing a quick algebra, plus an exponential across and then taking logs and then dividing by 0.9 should give us ln 24 over 0.9. And friends, this should give you 3.53 years. And that's it. Plugging in the value of t into the original p equation should finally give us roughly 102. So can you guys share that for me? Because again, these are model answers, but either way, the methodology should be fine. Now, let's wrap this up with part D. Yeah? Part D should be quite easy. What's it saying? So it's saying use the model to state the maximum value of k. Okay, so we know that as time progresses after the capital T is the maximum value t, we know that the number of rabbits decrease to k. So remember, k is just some random constant which occurs after you decrease infinitely. So we can simply say that as t approaches infinity, then capital P, the population, approaches its maximum population, which is k. I should really call it p max, so they should call it p max. So another way to say this is to take the limit. And again, if you've never seen this limit before, I mean, it's a very convenient tool which you use in higher level mathematics. It's pretty much substituting the values in. So we just write that the limit as t approaches infinity of the equation p. In other words, we substitute the t as infinity, or in the calculator, you can just put in a lot of nines. It's like 99999. I just put in about, I don't know, 5 nines. If you plug in 5 nines, you'll know that t to negative infinity actually approaches 0. So it's like 100 times 0. And likewise, over 1 plus 3 times 0. And 100 times 0 alone is 0. So you don't even need to worry about the bottom. Hence, 0 plus 40 will give you 40. So actually, in the long run, the population should decrease to 40 rabbits. Voila. And that's it, guys. I hope this video helped. And let me know in the comment section if you want me to solve any other problems outside this paper. I have plenty more videos that's coming up, and I should, hopefully have the rest of the C3 paper uploaded by the time, or it'll be uploaded after a couple of days. Anyway, take care, guys. Look after yourself, look after your family, enjoy your days, your evening, and let me know and have a fantastic day. And I'll speak to you all later. Ciao. Here we need to prove the following trigonometric identity. So before we do this video, we need to make sure that we have complete knowledge on trigonometry at least all the identities. So first things first, looking at the expression, we have sine 2x here and we have a cos 2x. So we need to know our double angle properties, okay? So just a quick note, what are double angles? So we can say that sine 2x itself can be expanded to 2 times the sine x multiplied by cos x, okay? So 2 lots of them. Whereas cos 2x can be expanded in multiple ways. So we'll leave it as is. Actually, to put the more general expression, it's just the difference between cos squared x and sine squared x. But these can be rearranged, of course, based on the sine squared plus cos squared rule. Now, one useful trick I recommend for any proving system is to always convert every single term here to sines and coses here. I'll show you why in the end. So right at the bottom here, I would always do a triple equal sign. And on the left hand side, I'll convert to sine cos, and the right sine cos. So let's look at the right. Tan x, we know it should always be is the same as sine x over cos x. Cos 2x, again, could be anything, but we're going to stick with cos squared version, yeah? Just for the time being. So until we can see where we're going with the left-hand side. Now, on the left-hand side, if we expanded this, so sine 2x only has one definition, thankfully, so it'll be 2 sine x cos x minus tan x would be sine x over cos x. Okay, so far so good. So hopefully my handwriting improves. Now, let's have a go, yeah? What do we have here? So, let's move on to the very first step here. So we can continue with the step we did here on the very first step. So this can therefore be exactly as written, 2 sine x cos x minus sine x over cos x. Now notice how they combined every term. So let's combine the terms. So we need to realize that everything is over cos here. So perhaps we need to multiply up and down on the first term here. There's 2 sine x by cos up and down. So we should have 2 sine x cos x, because there's an extra cos x, it'd be cos x squared all over cos x. And now minus sine x over cos x. Alright, not so bad so far. Okay, so next thing, what's going to be next? So now we can combine the terms here. So everything will be over cos x. So we're going to have 2 sine x cos squared x minus sine x all over, all over, give me a second, oh god, it's hard to do that, cos x. Now, before we get to this last step here, we need to observe. So here they somehow go cos squared minus sine squared. So looking over here, let's factorize the sine x for now. Okay, because sine x seems to be outside the bracket with cos x. So factorizing sine x, what do we get? So we get 2. No, we don't. So we get sine x outside. Inside the bracket, we're left with 2 times cos squared x minus 1. Okay, excellent. Now, we've actually got a solution. So one thing to know, one of the other equations for cos 2x is this. So we got cos squared x minus sine squared x. If we let sine squared become 1 minus cos squared, we will actually get 2 cos squared x minus 1. So yes, guys, this term right here is actually cos 2x. And that's it, we've proven it. And then we can finally say, therefore, this would become this term. And finally, this can be rearranged to be tan x cos 2x. And that's it, guys. This is my shortcut done. So recap, always convert everything into sines and cosines, yeah? Always convert them to sines and cos, because the reason why this will make your life a hell of a lot easy. But anyway, that's it for now, and I'll see you on part B. Okay, ciao. Okay, here we are, part B. So now we need to solve between the ranges of 0 and 360 the following equation. Now, the first thing I want to point out is that this is almost identical to part A's solution. For part A, we had a very similar expression. The only difference is that the left side was identical to tan x cos 2x. So what's this telling us? This is basically telling us that the left-hand side was identical, but that was identical to the right side. So we could actually assume that this whole side can be rewritten as tan x cos 2x. The reason why is because we cannot actually solve this. Or maybe we can, but it's just very long-winded and difficult. Now, doing this, we can instantly notice that instead of looking at both sides, we can instantly notice that they both have a tan x, which can be cancelled out, and we'll be left with just 2 terms, a 3 sine x and a cos 2x. Okay, so let's have a look here. So this means we're going to be left with, on the left hand side, so let's just rewrite again actually for the sake of it, tan x cos 2x, and this is equal to 3 tan x sine x, cancelling out terms. So let me just quickly cancel these out. So this goes and this goes. Okay, so now we're left with cos 2x equals 3 sine x. Okay, now you can't do much with sine x, but cos 2x is a double angle. So let's rewrite this into the other property. So the other double angles we had, so we solved the previous two. Cos 2x was cos squared minus sine squared. They can also be rewritten as 1 minus 2 sine squared x. So this is another version of the double angle of cos 2x. So let's replace cos 2x here with this sine squared x version. So therefore we're going to have, let's have a look, 1 minus 2 sine squared x, and this is equal to 3 sine x, and that's it. So let's put everything on one side, so it's going to look like a quadratic in terms of sine x. Okay, so plus and 2 sine squared across and adding 1, we're going to be left with positive 2 sine squared x plus 3 sine x minus 1, and this is equal to 0, and that's it, guys. And just to make it, if you're unsure, just let sine squared x be y, so we can have 2y squared plus 3y minus 1 equals 0. And now we just factorize as normal. So factorizing this, you can put 2y here, and you can put y here. So this will guarantee 2y squared. And now let's try. So the only possibility is to get 1 will be multiplying 1 twice. So let's just put 1 here and 1 here. To get plus 3y, let's see. Nope, not possible. So this means we might need to use the quadratic formula, it seems. Too bad. I actually thought we can do this in one go. Let me see if everything's correct. Yeah, everything's correct. So, alright, so let's get a new page. So quadratic formula is, so 2y squared plus 3y minus 1 equals 0. Therefore, using quadratic, we're going to have y equals, so the formula, we probably know the formula by heart anyway, so I'll just go ahead and do it, yeah? Minus 3 plus minus the square root, so 3 squared would be 9, minus 4 times a times c, so it'd be minus plus 8 over 2 times 2, which is 4. Okay, so this seems to be the solution, yeah? Yeah, that makes sense, because this 9 plus 8 is a prime number. Okay, so therefore your two solutions for y is going to be, for sine x, because y sine x is going to be minus 3 plus minus root 17 over 4. Now let's have a look. So I'm not sure if you get 1, 2 solutions, because it's my first time doing this as well. So if we're going to inverse this, so inversing either the negative side, so I'm going to inverse the negative side first and see what result I get. This should give us a, nope, you get a math error. You cannot negative the inverse, so you got to do minus 3 plus. So yep, there's only one solution. So inversing the positive solution only, you should get x equals 16.3 degrees. Whew, almost done. So that's almost done. So looking back, they won the range between 0 and 360. Okay, so we're gonna need another fresh page for this one. Okay, here we are, fresh page. So we got x equals 16.3 degrees as the first solution. Now using now to find the rest of the values, we need to use the cast diagram or the quadrant rule. So the cast diagram is this. So let's just make a simple cast. So let me just quickly do one here. So we've got one line downwards. So just make it look like an XY axis. Okay, now all we do is simply label each side with cast. So we're going to start from the bottom right corner. So it'll be CAST for cast. And because we got sine, we had a sine x earlier, we need to work with sine, and it was a positive result, so it's going to be S here, and A always stands for positive value, so that's how it works. Okay, if you worked with cos or tan, you'll be using C and A. If you worked with tan, you'll be T and A, because the sine is S and A standing for all, and they both have an angle of 16.3 degrees. To get the final solution, all you do is start from 0. So 0 begins here. A half circle is 180, a full circle is 360. So the length, firstly, to here is obviously 16.3. Now the length from 0 all the way here will be just before 180. So 180 minus 16.3. And this should give us, I should be able to do this mentally, shouldn't I? So gives us 163.7 degrees. Okay, and that's it, guys. That's all your solutions. Because it goes out 360, you can't really do more, because if you did another circle round, it will pass the 360, so it'll be 376.3 and so on. So yeah, And that's it. I mean, if you got any other questions, please let me know. If you enjoyed the video, please give it one big fat like and pass to your friends as well. Let everybody know, and I'll be doing more papers and more examples as time goes on. Other than that, I shall see you guys down the road, and ciao.